Again, so in this session, I would like to share you some of my knowledge and experience skills regarding ship resistance prediction. Just the first of a background, theoretical background to calculate ship resistance. When we have a ship operating in the water, resistance is probably the most important performance that we need to account for, because the water gives, mainly the water, also the air, but mainly from the water gives it resistance, prevent it from moving forward. So that's why we need a propulsion system for the ship to help the ship advance against the resistance. To accurately predict the ship resistance can help us to design the ship, equip the ship with appropriate propulsion systems. And if we can optimize the ship design, we can also save fuel consumption and reduce the emissions. So it's very important to calculate the ship resistance, and safety is one of the primary methods. So ship resistance, when a ship is advancing in water, it comes from two parts. In safety, it's pressure part and viscous part. The pressure part is, you can imagine when the ship is moving, advancing in the water, it will push the water aside, so it breaks the water, or we call it wave making. And the second one is when the ship is moving in the water aside the ship gives it friction, so it's a viscous force. So to accurately predict ship resistance in safety is actually to accurately modeling the fluid field, and then we would know how to calculate the pressure force and the viscous force. So this is the whole idea. Here I would like to first to emphasize the scale effect. So, in real life, the ship is very big. It can be 100 meters long, 200 meters long. So when we do experiments, we normally have a model scale experiment. And this scale will make the simulation to be quite different between model scale and the full scale, because it's not practical to have this full scale measurement, or we call it a state trial, every time you want to load the ship resistance. So normally we will build a smaller whole model, and like couple meters or even smaller, and put it in a towing tank experiment facility and to measure its resistance. However, this could bring some problem. There are two mathematical non-dimensional numbers, fluid number and Rayleigh number. The definition I'm giving here. So just to look at these two numbers, one is mainly governing the wave or initial force, and other one is governing the viscous force. So normally when we do experiments, we scale it down to the model scale, and normally it's according to the fluid number. So you can say the L is the ship length, and if you consider the ship length to be scaled according to the fluid number, in Rayleigh's number, the order of the ship length is clearly different. So it will make the Rayleigh's number to be very different in model scale. In other words, the fluid number and the Rayleigh number cannot be together equal in both model scale and full scale. So the force predict in model scale will bring an error when you consider in the model scale, in full scale. And to correct this, we need to apply some correction procedure. The International Towing Tank Conference developed a procedure called ITTC 1978, and it's a conventional method to correct the viscous force. So when I want to say this, because when we run safety, normally we run it in model scale to compare it with model experiments, because we have a lot of experimental data that we can compare for. And the ship resistance is easy to measure in experiments, but in sea trial, imagine is extremely hard or like unpractical to measure the total ship resistance for the full scale condition. Normally we need to measure the thrust of the propulsion system, and then do some calculation to convert it into resistance. So this case makes most of existing safety simulations in no matter OpenFOAM or other software was done in model scale. But in this slide, I want to mention that those results needed to be if we consider it in real life, in model full scale real life, it need a collection procedure. And also this gives us the possibility thinking about if we have more full scale sea trial data in the future, it's always the best to run safety in full scale directly because even we can scale the force correctly, the fluid field will be also different because the radar number is different, so the fluid behavior will be quite different too. So this is not only because resistance is not only the performance, it can be many others like cavitation will be introduced later by Nicholas. So this cavitation is highly sensitive to the what actually happened inside the fluid, and also some other application like hydroacoustic applications introduced by Tom. It's also impossible to use any correction procedure to predict. So so it's always the most ideal situation is to run the safety simulation in full scale directly. But I mean, for many reasons, so 90% of the simulation are still in model scale, but we need to be careful here. So today I'm going to teach or share my some of my personal experience. This will be based on a tutorial case, DTC Hall. You can find in your OpenFOAM tutorial multi-phase interform RAS DTC Hall. So here I will first of all I will need you to have a tour of this tutorial case together because it's kind of well how to say turned by OpenFOAM, and but I will need you to read some directors and tell you how did this been done. I think there's three parts: computation, domain, and boundary conditions, mesh, and Timestep. Those three parts are normally essential factors how we can make a safety simulation accurate. Inside the three parts, computer domain, boundary condition, a lot that's I mean valuable. Normally we have a common practice how to define them, and Timestep too. So I put a star sign here in the mesh part because 95% of safety problem or inaccuracy I had was I found that it's just a mesh problem. If I improve the mesh or I mesh it appropriately, and the problem can normally be solved. So I put a star here. And another reason is because the ship geometry is very complex. As taught by Ruben, he introduced how to mesh a submarine. Is kind of similar because the ship geometry has the similarity between with the submarine geometry. So the mesh part is very critical, and I will particularly introduce here. And then next, because this is a tutorial case, and normally we need to consider some other cases, like if I have a new case. For example, I want to replace the whole form. What should I do to adopt the case? What if I want to change the velocity condition? And what will be difference between model scale and the full scale, since I already emphasized it. And another point here, you look at the computation domain I draw here, the velocity is coming from inlet to the outlet. One of the things in safety problem we already learned is that in safety domain, the ship is not actually a ship inside domain. It was cut as empty inside domain. So it doesn't have any mesh inside the ship. It was cut and modeled as ore. So imagine we have some hole inside the safe domain and it's moving forward, and the hole will bring a mesh to distort with it. So a very common way to simulate flow problem is to fix the geometry. So we fix the ship inside the domain, but we make a water flow. So the water and the ship will have a relative velocity, which is u here, and this in real life, it's the same as you have u equal to 0, but make the ship advance. In this treatment, the hull or the ship is always inside the water, and we solve the fluid mesh, so the mesh will not be destroyed by the ship motion. So computational domain, just as we in the in previous slide, we introduced the computational domain in 3D, and then now we have a look at this. If you can follow my mouse, you can see the ship domain. I draw it like in this way. This is a plan view. Look from top of ship. So normally we need to leave some distance before the ship so that the fluid domain can be developed, and also longer one behind the ship. LPP is the ship length. So this is kind of non-dimensional, and we need some wider from a side ship so that the ship wave, if we go like this way, it will not reflect and influence our accuracy. So this kind of makes the sea to be like open sea. So it's like a infinity big in real life, but model it in this way. And these numbers are put here is my, how to say, my experience. So it should be a safe value, like the computational domain is sufficiently large to be considered as infinity. So similar to here, it's a profile view, and you can see there are some distant on top and some distant below the ship. So you consider this a deep water, and also the sky is very high. Okay. So about the mesh part, so in OpenFOAM, to solve a problem, any problem, you want to use as less mesh as possible, because you want to make the simulation as fast as possible, but remain the accuracy. So this lead us to think about, we only need to have this like, how to say, refine the mesh near the important part of the place. So this is a drawing, like you can say the mesh around the ship is very dense, and then it radiate outside, so it become more and more dense, and then when it goes to like the open water area, the result is not that important, so we can use very coarse mesh. So in this way, even the mesh around the ship is extremely dense, and the computational time can still be saved a lot and affordable. Okay, so to make it easier to demonstrate, I will just put a code here. Otherwise, I'll have to switch my screen to open the case file. So I try to copy most of the important code here. So block mesh open. So block mesh is kind of already be introduced by many previous presenters. So I will not say more detail about it. Look at this, how it writes in this way. It divides the domain into 6 blocks. You can say this X and Y are always the same for every block, but the Z axis is change a lot. So it defined somewhere here as a boundary, and then here -1 as a boundary, 0.0185 as boundary, and So in this case, it divided this into many different domains, like different blocks. This block mesh do, and then you can define different mesh density here. So if you see the block 1, and you can put here, x-axis, z-axis is 50 and 50, 40, 20. So, but x and y are always same. So in this way, we actually be quite cleverly define this, like in the waterline, the yellow and orange and the red and the green part to be quite dense, but the gray part and the blue part are mainly just the water and the air, and we don't really care about it. So it's quite coarse mesh. And in this simple gradient, it's like to make the mesh can change gradually from the top to here. So you can imagine 2.4 is very coarse, and come to this 1.6 place is dense, and also this -1 is dense, and this -16 is quite coarse. So this setup divides the computer domain into 6 blocks along the axis. High resolution is applied at the free surface region. Okay, just now we only defined the z-axis in this way, so we didn't refine anything in the x and the y-axis, since this is a very big computation domain. So the difference here is like, for z-axis, the free surface domain, the whole across the whole computation domain. So in block mesh, we refine the z-axis. However, for x and y, it's not that the important part is only around the ship. So we do this local mesh refinement to choose some box and then refine them, while this like kind of a global thing because the fluid surface comes from stretch from the inlet to the outlet, so it kind of needed to be refined globally. So this local mesh refinement, if you check the tutorial file, you will see a top set, so it's a defined region. Actions lam say 0, and it define a box from 2 points. So this 2 points is this point here and this point here. When we have these 2 points, and we can define a box. So this this figure is quite clearly show how the box is defined. Then this box is called say 0, and then in refined mesh dict we can have this set to be C0. So we tell this refine mesh dict we are going to refine it. We refined globally, so in the whole box and global coefficient. So this tan 1, tan 2 is x direction 1, 0, 0, and y direction 0, 1, 0. So this is tell the solver to refine the mesh in x and y directions. And one more thing is about this level is 1 means the refinement level is 1. So if we have a box and the refined level 1 is to divide into 4, actually in 3D will be 8 cells. So this refinement is kind of a lot. So because 1 cell will become 8 cell eventually. So so be careful, don't use too much of the level, because then it goes 64 actually in level 2. So normally I would just put 1 here. So this stuff refines mesh in the x and y directions. So now we have this so we can choose many boxes, like just not just one, because for example, we have one refined near the ship, and we can add another one refined a little bit outside the ship. So I will give more detail how to do this later. SnappyHexMesh, this page, this graph is from the OpenFOAM website, but I think it's really good to introduce what SnappyHexMesh really do. So once we put a ship inside domain, it actually have overlap with the background mesh, which is black block mesh and refined block mesh. So when we have a geometry here, it have an overlap, and this overlap, the ultimate aim is to cut everything inside this geometry to be empty, so that it's not calculate any fluid solutions, but it's considered as a wall. First step is called calculate mesh. So it localize refine the mesh around the object body and the edges. So you can see when it identify overlap, it will do some refinement here. So eventually the refinement will be across the overlap edges. And make it, this step is called calculated mesh. And then slab is to cut all the mesh inside. Okay, but it, you can say there are some edges clearly it's a wrong result, so we need to smooth it a little bit. So we cut those edges too and make it to be like this. But still, to better moderate the boundary layer, which is really important for the viscous force, we need to add layers, refine the mesh around the body. So will be some layers added here. I think maybe it's necessary to have a look of the actually SnappyHexMesh dict inside the case. Please tell me, am I on my screen or still in the presentation?
Still in the presentation, Lou.
Okay, let's go to a screen. Okay. Am I speak too fast?
Now it's fine. We can see that.
How do you think about the pace, Nicholas? Is it okay?
Yeah, it's fine for me at least.
Thank you. Okay, quick tour. So I want to copy as many code as possible to the presentation so that we don't need to switch. But I mean, this SnappyHexMesh is quite important, so I want to give a bit more look. So this three steps as I introduced, and then turn them on to be true, and but if sometimes you think it's important to do one of the steps, then you make it to be false. And here geometry should tell where the geometry is stored, which normally is so. When we run a case, we study a tutorial. I always look at the all run first to know what it actually do. So this all run make a new directory called the tree surface, and then copy something geometry STL file to the constant tree surface. So which means a several shape geometry. SnappyHexMesh will identify and find the shape here. So which means if you want to change your geometry, then you put it under this tree surface directory, and SnappyHexMesh will find it. And then remember about this different names. So if you use some different geometry, just change it accordingly. And then the first step, and then you can set some detail. For example, max local cells, which is if you are doing parallel, then it's max on one processor. For the total cell number is 2 million set here. So what we need to do here, because when we do SnappyHexMesh, you need some refinement here, so which can cause the you know, the mesh can be crazy. But if you don't want to be too large, you can set a max number here and the refine level. So refine this is something like you spend a lot of time when you trying to refine the few cells. So if you have like 10 here, so which means when the it has less than 10 cells to be refined, it will just stop. Sorry. I mean, there's a lot of instruction here, which is quite clear. So I would be a little bit fast. Refine level 3. So I already introduced refine level. Features is to detect some edge of the shape. So it can be some very curved or very sharp part. So it's features to identify them, and then will be the particular treatment will be applied there. And then surface refine, you know, some edges, or like how many, when it's larger than 55, you do refine. So so here it's a kind of important location in mesh. So you should choose somewhere outside the ship. For example, if you choose this inside the ship, it will keep the mesh inside the ship, but delete all the mesh outside the ship. And then we have a container. So we need to delete the mesh inside the ship. So always choose something outside the ship, because when the ship geometry change, sometimes the coordinator become different. Okay, smooth. This is quite straightforward. At the layers, very straightforward, and I will have a particular slides to introduce about this add layer controls, because it's really important when we predict ship viscous resistance. So bear with me, I will come back to here later. Now I'm going back to my slide. So I'm with my slide, right? So basically, after we have done this, and then the ship was cut from the whole computer domain. So you can imagine we have a big computational domain with x axis, y, and z axis refined in some regions we want, and the ship geometry was inserted inside the ship, inside the domain as a whole, as a wall function. Let me see if there are some questions. The mesh in this tutorial generate best hex mesh collapsed in the after region of the ship. I find it very hard to get a nice viscous layer along the whole ship. Do you have any suggestion? I don't think the tutorial will collapse because if you just type all run, it should run quite smoothly. I do have some results already. I finished it because it takes like 1 day, 2 days to finish it. So I finished it in advance, and because the OpenFOAM tutorial are all like well established. So I think if you just do all one, it should not collapse. Okay. If you have more questions, please type and I will answer it when I can. So this UCL has been taught by many previous presenters. So we divide this domain to be 2 regions, which is alpha 0 for air and alpha 1 for water. Any value between 0 and 1 is for fluid surface, and it's to solve some transfer functions. The density of like for example for this cell is 0.4, so it's the density of this cell will be, because water density is 1000 and air is 1, so this cell will be like 400. So what we do here is we have ship domain. Oh, nice. This function I never tried it before. And define it into 2. This is water and this is air. And when it's a still static water surface, we shouldn't have any waves. But when we have a ship here, so the ship will have some change. So will be some cell value with different how to say different some value of alpha between 0 and 1. How to set this? Okay, go to next slide. So this will always stop here. Can I delete it now? Eraser. Nice. Okay, so how to define the water depth? Goes to the one file called the set field and then define water depth. So you can say the default field value is alpha water equal to 1, and define the region. The box is the same as we defined before, which means this is actually infinite. So this makes it like infinitely deep and wide, but we have this 0.244 at the at the water line, and this patch is about the surface, and this region is the cells below. Yeah, I think well, why do we set 0.0244 is because when we design ship, it will have a designed water line. So if in the case the ship the water line is at 0.0244, then we define the same water line level at the in the simulation. So it's quite simple. The ship will be somewhere here. Okay. Okay, let's go. So I think one of the most important is the water velocity, and this is also very simple to define. So if you open the 0 and you can say a U folder, a U file, and then you open it, you define U min equal to 1.668, which is your water velocity. So in this internal field, it's a uniform to be this value minus down, because it comes from the right hand side to the left hand side, so it's minus. This is kind of the most or the only like value you often change because it's a water velocity. Because when we do the test, we normally have to test a range of different velocities. So which means this value you can change it here, and one of this outlet function. This function it's quite important. It makes the outlet flow to be water flow to be the same as interwater flow. So if we have a domain, we have interwater flow, and if outflow water flow, the mass of the water doesn't equal to interwater flow, it can cause the fluid surface to increase or decrease. So it's quite crazy in that case, and it happened quite often. So this boundary condition defines the outlet water flow to be always in same as the interwater flow, so the water line can keep that at the constant value that we want. Atmosphere, nothing special. Some like static pressure condition and the whole wall. Although it's a moving wall here, we didn't use dynamic mesh, so it's you can consider it as a fixed wall because and the value of velocity is always 0. So time, solver, and function object. So in this tutorial case, the solver lamp interform Minhao already gives a lot of details on this. No need to introduce more. Start time, then the time, so we run it for 4,000 seconds, and we solve it for each second, so we run for 1,000 time step. Write interval, so we save results every 100 steps, so use a reasonable value here, otherwise your storage will be crazy because this case is quite large, it's huge, so we try to save as less results as possible. This huge right, I kind of not remember because I didn't change everything here. I think it's kind of about the format, how you save it. It doesn't really influence your computation result. And some precisions is how many value you have behind the dot. So runtime modification is if you want to change it set in during the case is running, because for example, if you run it overnight, after 1 hour you want to change a little bit to some, you know, at the beginning you want to use small time step, at the end you want to use larger time step, you can change it. But if you set it to low, even you change it, it will not be effective because it will always use the same setup when you initialize the simulation. However, I have highly recommend you to use this adjust time step, which is you set a current number to be maximum 1 or something. The current number will automatically calculate a time step for you. So I will maybe draw something here. So U is the velocity of the, actually, let me to be more clear. Inside the core domain, we have many mesh. So each of the mesh should have one column number because it has a velocity here and it has a delta x here, right? So in how to determine this column number, normally we have the maximum column number, which is the column number maximum value inside the whole domain. So so the column number will have so the delta t equal to, sorry about handwriting, column number delta x and u, and the delta t should be smaller than the minimum value of this if you set this to be 1. So this is quite good because sometimes in the complex place like near the ship, this can be quite smaller, and then your time step will automatically become smaller when the fluid domain is complex. So it's very handy to use this adjustable time step. A normal practice, you may read online, a lot of places recommend to set this to be 1. However, a personal experience said model scale, this is recommended to be 1, but in first scale, I usually can do this at 10 and it doesn't have a problem, but I cannot guarantee. I just tested by myself in first scale simulation. This time column number you can set at 10. This is just my case, but the model scale or most of the recommendation online, you will find to set this at 1. So but I think you could try 10 when you run first scale simulation. Maybe it can save you a lot of time because it's kind of 10 times faster than 1. Okay, function force. This force is something to help you to automatically plot the force against the ship. So to be very clear here, even you save the result every 100 time step, the function object always write it every 1 time step. So it can save a lot because you don't need to have the domain to be every 1 time step. So you save it at 100. It's quite big, but this is just create a table file, and then you can save the results force to be every 1 time step because this can change a lot between Timestep 100 and 200. So yeah, so use function object to get the results is much more efficient than use this write function to get result. Though info is the water density, and you log on Timestep output. Oh, here is one. So that's what I mean here. Central rotation is how to say, inertia property of the ship, so it's kind of from your CAD. Okay. Erase. Next slide. Oh, I have some question. Let me see. It's always been hard for me to get desired information names for so many domain which mesh. Okay. Yeah, I have one slide for this true pen. I will come to this just in a bit. Okay, next page. So verification and validation. So after we run the case, you will see a file like this. Have to go back to screen again. It's a mess. Okay, I need to open this. So
yeah.
So if you do all run, and you will get exactly the same result here. I just put it here because it's we don't have time to run the case during the tutorial. So I copy it and just show you here. So in this file, this picture I already made, but forget about this. Just look at everything before T. So this will save a file for the force, and Px, Py, Pz is the pressure force, and X, Y, Z direction. Yx, Y, Z is the viscous force in the straight direction. So we want to know it's the pressure force in the X direction and the viscous force in the X direction. So we calculate and this add it before at this, and then plot it against time, and it will be like this against time, and it's finally come to some value like around 15. Around 15, it's the result. And one important thing here, remember the ship is symmetric, so normally we just put half the ship inside the domain and calculate force and times 2 in the final result. So so the total ship resistance here should be 30 something, maybe 30.5. So here we are good to have a look of the experiment paper I already found for you. So this paper introduced a towing tank test for the DTC ship. I will put this on Dropbox. I'm not sure if I already did, but you will get it. So so this case introduced how to do the experiment for it. Okay, but I mean, we care about resistance value, and then here, so we used this velocity to be 1.668, and the resistance value is 31.8. The Excel calculator here to be 30.5, so it's kind of 1 Newton less than experiment, but it's already, I would say, very accurate, because normally for safety and experiment there are some uncertainty. So if the deviation is less than 10%, it's already quite good. So this is also shows like safety is a very powerful tool to do this simulation. Okay, so for this, I want to say a little bit more about this mesh. So when we have different cells, it's easy to a common practice to this mesh convergence. So if you have the total rate value, if you increase the mesh in some range, you would say it will be some trend like this, except your mesh is too coarse. But when it's come to the convergence point, it will be something like this. When you continue increase the mesh density, it wouldn't change the results that much. So. And this is also why I recommend to use Coulomb number to do this, because when you change the cell size, you don't need to calculate the time step again. It's automatically done for you. So I highly recommend if you open the adjustable time step. And here, so this is the value. It's the final value of the total resistance the way I convert into the coefficient. But it's really common that I show this in the middle. It's a good example and bad example about the convergence. Even you see this average value converge, sometimes it doesn't converge in the time domain. If you run it in 200 seconds, this may be acceptable, but you can see it oscillate a lot, but this one is much better and come to a straight line. So I mean, it depends on how fine, how precise your simulation want to be. But I mean, this is acceptable. But most of how to say, if you want to be ideal, you would like to see a straight line at the end, so that you can say, okay, I got the really convergent, not just like from this picture, because it's kind of not very clear if you cannot clearly see this oscillation. Then after this is called verification or validation. Two terms are normally confusion, but the verification is how you value your numeric setup and to check if you're convergent. But the validation is specifically when you only compare with experiment, use the validation. So I plot some of the results I did previously. Just an example, like I shown you in the Excel file. OpenFOAM or other safety software, it's very accurate, I would say, to predict open water ship resistance if the setup is good. The deviation should be less than 10% if we did a good job. Okay, come to here. It's some my personal recommendation for modern waves, because it's already asked by some questions in the chat box, so I would like to give suggestions here. Again, I'm not guaranteed that my suggestion would be perfect, because so many researchers and I'm not the one of the best probably. So, but this is, I have done a lot of tests in recent years, and I would like to give this recommendation to some of you who want to model ship in the future. Maybe they will be useful and help you to speed up your configurations. The left-hand side is the simulation I done, and right-hand side is the sea trial photo, and you can see the wave pattern compared quite nicely. And this is very important because the wave force is really important for the ship resistance. So how to model this wave force correctly? This is my recommendation on the mesh refinement. In the tutorial case, it refined for 6 regions, but I will explain here why I only use 3 regions. Here, it's I found that interaction between water and the bow at the head, the bow area is really important because it radiates afterwards. So I would say normally use a circle to refine the mesh here, and another circle out to be a little bit coarse, and then another circle to be a little bit coarse, because interaction here is very critical. And then this triangle region, it's depending on the Kelvin wave angle. So Kelvin wave angle is 19.47. So this angle should be slightly bigger. I use 22, 23, 25, doesn't matter, but it should be slightly bigger than the Kelvin angle of the real ship. And then this is a region, second region, third region, and also slightly to be larger. Okay, and this mesh density in the most inside the region, so this is all randomized, so you can see how large should each region be. Again, this is my personal note, so maybe be something even better or better than this one. But I normally use delta x and delta y to be 20, how to say, 5% of the b divided by 20. I'm very sorry, I need to revise this. Do it. So b divided by 20, yeah. B is the beam of the ship. So here at this, we should have 20 meshes in x direction and y direction. In here, we should have 10. The density should be b divided by 10. And we use a slightly larger and radiate towards our side. In this place, I normally have this T to be the waterline. So this is the draught of the ship, and I use 0.3, 1.2, 2.4, and this also run. I did a mistake here, but it's easy to understand how to do this. So really tends to be here because the free surface wave will happen here, and so you can't. Why would I do this generally increase? It's because it's impossible to suddenly become extremely large, and then you have a very small mesh here. It will cause I would say sometimes crash, at least in accuracy. So it should be always increase slightly, and then come to a very big place. Okay. So this is one. Okay, and okay, I have the slide. How to model the boundary layer is asked in the chat box. I'm going to answer it here. So in this boundary layer problem, so this is a ship hull, and this is normally the hex mesh we used outside the hull, and there are many layers here. So these layers should be gradually increase from this to here, and how to so this comes up to several questions. What should be the total thickness of his? What should be the first layer thickness? What's expansion ratio of this mesh from layer by layer? So a very common practice is the y plus value. So this is the Rayleigh number, ship length, and this h is the first layer thickness. Again, if you read most of guideline aligned to recommend y plus to be less than 100 for runs. Not to mention Tom's LES, something less than 1, I think, but this can be less than 100 for model scale ship. So here you can calculate h through this equation. And again, personal experience, when you have a full scale ship, y can be 1000, but no guarantee. You could try to increase the y plus when you have a full scale ship. So how many how many number of layers? And normally what I do is I calculate the cell density here, okay, and try to make the final layer to be similar to this one, so that it doesn't cause a big problem. So it increases gradually until it's similar to this one. So the layers can be 10 layers or something less. I'm not sure if the 3 layers probably not enough for some place, because when maybe enough for this kind of geometry, but when it's have some complex region like near the propellers, I think maybe you need to be careful to increase this value. Expansion ratio 1.5, I think is very good. Normally I use 1.52 and it works quite well. So I mean, this setup is for you to explore, and I provide some recommendation for the wave and the west coast part, because I think it's the most important one. So I provide some of my personal suggestions. Hope it's useful. Okay, I think this come to my end of my presentation.